Hello. Many of you have been involved in using MATLAB to try to model the current pandemic in New Jersey. So school is over, your projects are in, but I think it'll be a lot of fun. Maybe fun isn't the right word. It would be interesting to continue to track the pandemic throughout the summer and see how our model applies. So that's what I plan on doing, and I'm going to invite you all to continue to follow. So I want to go over some of the changes that I've made as more information has been coming in. So I'm going to share my MATLAB screen with you. Okay, so here we are inside of MATLAB. So let me show you some of the things that I've changed in this model. Okay, so we have a matrix. Let's see, where do I have this? For the number of deaths in New Jersey. All right, so this is actually taken weekly from a government source. It actually was off of the Wikipedia page, but that is linked directly to a government source. So every Friday, we look at the number of deaths. Okay, so the first data point where that's relevant is March 20th. And so in the matrix, that was week 11. Okay, I'm making January 1st basically the origin of all of this. So in the 11th week, there were 11 deaths. And then in the 12th week, we had a total number of deaths. This is not new deaths. This is the total was up to 108. By week 13, that total had grown to 646. All right. So these deaths are actual data from New Jersey. We have data all the way up to week 21, which is 11,500 deaths. All right. Now these are entered in matrix form in MATLAB. A quirky thing about MATLAB matrices is you just enter them in one long line. Wherever you have a semicolon, you can see that in these first two numbers, that's telling MATLAB that you've gone to the next row. So that first semicolon says that the 1111 is on the first row. The second row of the matrix is 12108. The third row of the matrix is 13646. So while this does not look quite like a matrix as we would see it, that's how MATLAB reads it, and it avoids needing 21 lines, well, 11 to 21. That would have taken about 11 lines of writing for the matrix, which would be an efficient use of space in the computer program. So given that we'll add a new number every week, we would not want to add a new line every week. So matrices are entered that way. You can have a comma between numbers. So the 1111 could be 11 comma 11. That keeps you in the same row of the matrix. As soon as you put the semicolon, it takes you to the next row of the matrix. And as always, the three ellipses, the dot, 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 whoops, sorry. The dot, dot, dot just means you're continuing the line. So technically, this matrix of death counts is all written on one line as far as MATLAB is concerned, but the semicolons allow it to have the different rows of the matrix. Okay, so we have the death data in there directly. And what we did, or what I did, was I carefully looked at the data for deaths, and in plot choice 5, that's the plot choice for deaths, I picked A values that would match the data. Now it's hard to see that right now. The percentage of deaths is well below the 8% that I have shown as my vertical axes. So let me bring that down to 0.00 to 0.5%. And if I do that and look at the data again, you can see, let me also not look at 80 weeks worth of data. Let me just look at the data where we only have values out to 21 weeks. So let me set the maximum time to 25. And you can see how the data is matching the curve. I may want to adjust my numbers a little bit, allow that to come up a little bit higher to match those later values. So I may play around with my A values in the beginning part of this in order to match the curve a little bit better, okay? But I'm getting a pretty good match of the existing data. I think I will go back and tweak those numbers and get a better match there. Okay. So the second thing that you may notice, let me go back to plot choice 6, and let me make my maximum go back up to about 8%. All right, and let me map that out for 80 weeks. So the second thing you can see is this dashed red line, okay? And you can see in the legend that is ITH. So remember, that was our threshold infection rate, all right? Where if we go over that, we have basically broken the medical system. So you can see that right around probably about week 17, or no, that's around week 15, I think, is this first peak. Okay, that's when we were getting very close to crashing our medical system. We clearly stayed under that, but we were approaching that level. But I've programmed it now so that the threshold is going up because we were importing new ventilators, we were increasing hospital capacity. So I am assuming that we would be better prepared for a wave of infections in the future than we were back in March. We were clearly very ill prepared in March, and our ability is going up. So I made I threshold an increasing function rather than just a constant value. So to accomplish that, I give it an initial amount, right? And that's sort of selected to make sure that we didn't crash the system early on, because we did not. We know that that's true. So that was chosen, and a rate at which the threshold is increasing. I'm assuming that we could increase it by 3% over 52 weeks. So that M value is a slope. And then right in the beginning of the calculation section, I create the line for I threshold at every single time value. Okay, so for we're counting time in hundreds of weeks. So we have a new threshold value for all of them. And then later on in the code, we can see right here in this if statement, if the infection is below the threshold amount, better things happen than if the else is if we crash the system. Okay, so bad things happen when we crash the system, and the number of deaths will be significantly higher. Okay, so we simply have changed this. I threshold now has a value at every time, so that governs that statement. Okay, the if statement for whether we crash the system or not. Okay, so the next thing that we changed is there is now a matrix of A values. So you may remember in your code, let me create a little more space here. You probably remember in your code that we had maybe 3 different A values, A before intervention, A during the interventions phase, that was basically when the stay-at-home orders were issued, and then you picked one more A value for when we opened up the economy. All right. Now, in order to match the data, we're allowing A to take on any value at any time. Since there will be so many A values, we don't want to have a series of if-then statements about, we don't want to have, before when we had 3 different A values, we had a series of if statements about whether we were in the first time, the second time, or the third time. That would be horribly inefficient at this point. So we allow new A values to be created for every week, or even you could have fractions of weeks. Okay, so let me show you what this means. This first set of numbers means starting at week 0, we chose an A value of 5.5. That's probably a bit high, but we really know very little about how the virus started and when exactly it started. So in combination, the I0 value that was chosen actually ends up being a fraction of a person, because on January 1st, we might not have had anyone actually being infected. The starting scenario is also complicated because people, probably new infections were being brought into the state at regular intervals. So it's very hard to tell exactly what was going on in the opening. So we simply want to pick a value for I0 and what was happening at the beginning so that we start to match up with the data once we have data for deaths. All right. Then we have here starting at week 12. That's basically when we left school. I drop the A value not immediately down to 0. I drop it over a couple of weeks down, okay, from 4 to 2.2 to 0.8 to down to 0.5. 0.5 is very low. So I figured by week 15, we had actually reduced the A value a lot, and that was able to match the data pretty closely. And then by week 17, we had brought it down a little bit further. I'll probably further tweak these numbers to match the data a little bit better. But these numbers here represent what would have been happening during the, for where we have data, right? And then from that point onward, I'm speculating as to what might be happening now, okay? So week 22, we don't yet have data, but I'm assuming that because that was about Memorial Day weekend, actually a little bit after Memorial Day weekend, I'm assuming by week, you can see the numbers are starting to go up. By week 20 and 21, the A values are actually going up a little bit because we had begun to open up. Since we're opening up further and further, I am speculating that those A values will just continually creep up. All right. Now, since I don't have specific time periods, what I actually did is I put in a counter to say which A value we're using. Okay. So we start in time period 1, but you can see further down in the code, there's an if statement about the counter. If the time counter is less than, this is just saying that we're before the last time period. This is really the critical line of code. If the time we're on is greater than what would A, TC1, and column 1 be? Remember, the weeks are in column 1 of the matrix, so this is column 1 here. And if we have TC plus 1 would be the next time value in the matrix. So if our time has reached the next time increment, we're going to step up our time counter by 1. Okay, so in other words, going back to my A matrix, once the time reaches 12 or exceeds 12, we switch over to an A value of 4. And then once the time has reached 13, all right, the time counter will go up 1. And so then instead we'll take the third A value and so on. So we have a counter to tell us which phase we're in, and then we'll pick the appropriate A value that goes with that phase from the matrix. All right, so we can have any number of time increments now, which is good because the A value, the transmission rate, is going to keep changing every week depending on how much the economy has opened and how careful people are being. And when we have social unrest and people get together for a protest, that obviously will change numbers. So we can track this week to week and change our numbers every week. All right, so we will slowly change these sort of speculated numbers into numbers that match the data over time and see what happens when we do that. Okay. Another thing you'll notice in the graph, we know what happened. Okay, certainly we have data for the deaths everywhere to the right of the black line, the vertical black line here. So that region is white as usual in background. So that's the kind of the normal background. That's showing us, what the graphs look like and what our model would look like for the region in which we do have data. All right. The shaded in background represents the region where we are speculating, right? We are using our model to predict the future, which is the only reason to build a model is to make a prediction of the future. It's easy to know what happened in the past, but we're going to, we're using our, making reasonably good guesses for what A would be in the future. We're trying to predict what would happen. Okay, so most experts predict we will have a second wave. The question is, as we open up the economy, the question is, how big will that second wave be? When will it hit its peak? Will it go over the infection threshold for hospitals to be able to handle the infection? So all of those questions are questions we would want to know answers to. So this is like predicting the weather, all right? So we know what happened in the past. We know exactly what the weather was in the past 5 days. We're trying to extrapolate outward and determine what the prediction, the forecast for the future is, okay? So you can see right now we're probably nearing the bottom of the infection curve because the economy is beginning to open up. It's very likely that we will see a rise in infections. That would be normal. We just don't want that rise to be too quick. We will not see it continue to go downward as we open up the economy. So we're probably near this minimum around the 22-week mark right now. We don't have data for that yet. But I suspect that we will, in fact, have a minimum right around 22 weeks. And if it's not at 22 weeks, it'll be close to that. And then we should see an upward trend from there. All right. We're speculating how quickly it will go up. But interesting things about this is we can see that if we do go up for a while, eventually even though the A values kept going up, the virus will sort of reach a second peak. So we're very interested in when that will happen. Will it be right as school is beginning to open up? Will it be closer to Christmas time? Our model will get better and better at predicting where that second peak will be as we have more and more data to match. Okay. The last thing I want to go over in this video is I have two different models. Okay. You'll see this model is called the 005 model. That represents a death rate of 0.005. Okay, so this is assuming that 0.5% of people who get infected will die rather than recover. Okay, and when I say recover, I mean become immune. All right. The other model that we're working with is the 001 model. That's assuming 1%. So I believe that's kind of where we left off in class, was assuming that there was a 1% death rate. The problem is we have no idea how many people actually have been infected, and we have no idea how many people are immune. Okay, so in the 1% model, when we got down to the part of the code where we're deciding how many people will recover and how many people die, we have a number 0.99 for the rate at which they're recovering, and a number 0.01 times the c-value times I for those who are dying. So you can see that's a 99% recovery rate and a 1% death rate. So as people leave the infected pool, they go either into the pool for recovered people or the pool for people who have died. We have 99% recovering and 1% dying. If we look at the same part of code, and that also translates down into once we crash the system. If I look at the same part of code in the 5% model, it just has a recovery. Whoops, I should look up here at these lines. That's before. We're going to try not to crash the hospitals. So we can see the 99.5% of people recover instead of 99, and only 0.005 die. Okay. Now, there are consequences to those two models. I will talk about those in the next video.